So I want to quickly go through the answers to the rest of the problems. I'm going to rush through them just because I need to cover this in 15 minutes and make it as quick as possible. So when you have a hammer hitting a nail with 2,000 newtons, you have friction between the nail and the wood is 1,500 newtons, and then you have the other information. So just very quickly in terms of interactive diagram, you have what looks like my ink tools here. You have a normal force here. You also have a frictional force here. You have gravitational force, and you have, in this case, an applied force. For this one, there's no normal force. You do have an applied force. You have the gravitational force and no frictional force, okay? So in that case, what I'm asking for this one is that you are going to draw an interactive diagram for those objects, okay? With that said, I have here my nail, and here my hammer, okay? To start off with, we have a gravitational force. The hammer is 1 kilogram, so if I do my conversions, the hammer to the earth, 1 kilogram times 10 to the 10 meters per second squared is 10 newtons. It has no normal force at all because it is not sitting on a surface. Oh, I will erase that. I'm so used to doing a normal force. We have the nail, which is going to have a smaller vector that also has gravitational force. It seems to have a force of a mass of 0.01 kilograms times 10 to 10 meters per second squared, giving us a 0.1 Newton force, and this is Fg nail to earth. Okay, so now the nail is sitting on a surface. For that reason, it's sitting on the board. We're going to have an Fn of the nail with the board, okay? And because it's sitting on there, this also has to have 1 Newton of force. We know that the hammer is applying a force, and this is where the breaking down your force pairs is helpful. Our two objects, they're hammer and nail. Then I say to myself, the hammer is pushing the nail down, so it isn't applying a downward force, so the nail is being pushed down. In this case, I would draw a large vector, and I was told that it is pushing down with 2,000 newtons of force. So the nail is experiencing a push-down force of 2,000 newtons. At the same time, I'm told that it has a frictional force, if I go back to my problem, of 1,500 newtons, okay? So this is going to be force friction of nail to board, and this is my applied force of nail to hammer. So just to review again, we're saying that the nail is pushed down by the hammer with a force of 2,000 newtons. The frictional force, which is opposite that, if you look above again to what is being said, it had a frictional force of 1,500 newtons pushing up, or the opposite way. Having said that, if we know that you have 2,000 newtons of force of the hammer pushing down the nail is pushing up the hammer with the same quantity of force. That's 2,000 newtons. This is going to be Fa, hammer, and nail. And that is all that you're going to be putting for the hammer, just a small gravitational force and a large large applied force. Okay, going through the next problem. The next problem is going to have also an interesting vector. This one I'm not going to do the interactive diagram again because I need to cover this in 15 minutes, but I will do the force vector for the arrow. So for the arrow, we ask ourselves, is there gravity? And the answer is yes, there is gravity. So we have an Fg force of arrow with the earth. And if I look up here, I believe that the arrow has 0.05 kilograms. So if I multiply it by 10 times 10 to the 10 meters per second squared, I should have a force of 0.5 newtons. All right. Then next, I know that this arrow is accelerating over here at 100 meters per second. So here's my acceleration. I know that force is mass times acceleration. So the force of the arrow, the net force of the arrow, is its mass. So we have 0.05 times 100 meters per second squared. And because of this, I know that my applied force applied for the arrow to the bow is going to be 5 newtons. Because if I do my calculations, 0.05 times 100 equals 5 newtons. I am going to say that there is no normal force. The arrow is not sitting on a surface, and there is no frictional force either. So this is my force diagram for this one. I simply have gravity and applied force. Remember, I calculated my gravitational force using F equals mg. I only use that formula to calculate gravitational force. This applied force, remember, is F. It is a net force, but because I don't have frictional force, it is mass of the arrow times the acceleration of the arrow. All right, next one. We have the ice cream cart vendor. This is so similar to the one that we have done as an example. I want to just again do the force diagram so I can make sure that I give you all the information. So just so I can write this information down, it looks like the cart has a mass of 40 kilograms. The acceleration of the cart is 0.6 meters per second squared. And looks like the mass of the person is 50 kilograms, just so I have this as a reference. Remember, I always want you to write down the values that you know. It makes all the difference in making this easier. So you're going to create two force diagrams. My apologies, this should say object. I hope that you recognize that. And in this case, I have my man and I have my cart. So a couple of pieces of information that I have here. Let me see if I check my friction. If I talk about friction, it says the cart has no friction, but she does. So we assume that there's no friction on the cart. And if I look at the cart, it is being pushed this direction. So in this case, the man is pushing, let me erase this. Looks like the man is pushing the cart forward. As a result, the cart is being pushed back. So I know my FA force is this direction. My FA force for the man is that direction because he's the one who's doing the pushing. So I'm going to just label that FA cart to man. This is FA man to cart. Okay, I know I have a gravitational force as always. So that's Fg cart to the earth. I have a gravitational force of the man to the earth. The man is on a surface, so we know that we have an Fn force of the man to the ground. We have a Fn force, normal force of the cart to the ground. I clearly said above that there is no friction for the cart, but the man does have friction. And remember, he does just because he needs to move that cart forward. So let's focus on, again, which one is the force diagram that you know the most information of. That's the one you're going to use in order to figure out your applied force. So The cart, let's see, gravitational force for the cart is going to be 400 newtons. How did I determine that? Just as we've always done, F equals mg. That's always gravitational force. I've used 10 meters per second squared there, along with his force, which is, his mass, which is 10 kilograms. Okay, so that means that his normal force is 400 newtons. I know he has a net force of 0, and a frictional force of 0. So that means that my applied force is going to equal my net force, okay? So for that reason, I can do F equals ma. I know that his mass is 40 kilograms, and the acceleration looks like it is 0.6 meters per second squared. And if I do the calculations for this one, it looks like I have 24 newtons, okay? So, in that case, I have 24 newtons of force that the cart is being pushing back. Okay, the man, we know that if this is 24 newtons of force, then this has to be 24 newtons of force, okay? The man, because remember, these are equal. The man's gravitational force is going to be 500 newtons. His normal force is going to be 500 newtons, just as we've determined before. But let's see what the net force is for him. So the man is also accelerating 0.06 meters per second, but he has a different mass. Remember, F net. In this case, it's going to be 50 kilograms, his mass, times his acceleration, which is 0.6 kilometers per second squared, which works out to be 30 newtons of net force. That's the key. That means that the difference between these two vectors has to be 30, in which case this is going to be 54 newtons, because if I subtract these two, they have 30 newtons. All right? So this is how you would solve this one. All right, so quickly, moving on to the next one. I only have 3 more minutes in this video. Same thing, we have, in this case, a tow truck. You have force diagrams. Let's get the quantities of what their masses are in this one here. And it looks like 2,000. Okay, 3,500, 2,000. Okay. So the truck, 3,500 kilograms. Car, 2,000 kilograms. And I have acceleration of being 2 meters per second squared, and a frictional force from the car, Fc, being 1,000 newtons. So I'm going to go off screen, finish this off so you can see the results, and then kind of talk you through them. All right, so here's a setup with the items that I know, and I'll work on the ones that are a little bit more difficult. So again, which one of these do I choose in order to calculate the applied force? Again, choose the one where you know most of the information in terms of the vectors. So take a look here. I have 3 pieces of information. I only need to find one. This is the one that I want to use to find my applied force. This one only has 2. So I know that net force equals mass times acceleration, and we're going to base that on the car. The car has a mass of 2,000 kilograms. The acceleration is 2 meters per second squared, so I do that times 2 meters per second squared. I should have a net force of 4,000 newtons. So with that said, it looks like I have, though, a frictional force of 1,000 newtons. Remember, this is net, okay? So what would be my applied force? Well, I know net force is applied minus friction force, or vice versa. As long as I get a positive number, it's just the difference. So this applied force has to be 5,000 newtons. If I know the applied force of this is 5,000 newtons, I know this applied force, thanks to Newton's third law, has to be 5,000 newtons as well. So now I've got the third one. What is my frictional force? So again, I know that my net force is mass times acceleration. In this case, my mass is 3,500 kilograms times 2 meters per second squared. That means the net force should be